now that we've considered potential and potential energy in general, let's now try to make things a little bit more concrete. Let's take these very powerful energy concepts that we've developed and now apply them to a new electric device. The device that we've been mentioning a little bit in our recent discussions, the capacitor. And in particular, we're going to be looking at what is known as a parallel plate capacitor. So it has this device has the following structure. I take two solid metal plates, one like so, right? They have a certain thickness to them. These are solid plates, so I'll hash that in, that's solid. And as the name parallel capacitor suggests, I take two of these plates, one below the other, in a parallel arrangement. So I'll have my other plate down here, down below, like so. He's also solid. And then, so that I can actually access this thing as some type of a circuit element, I'm going to need leads that connect me to the outside world. So there's going to be some wire up here, and I'll call this connection point, this junction point B up there. And down below on the lower plate, I'll connect to the outside world from a point A. And to define the specific geometry of any particular parallel plate capacitor, we're always concerned with the separation between the plates D and the area A of the plates. And both plates will have, of course, equal area. Now, the way this device functions is charges then we can transport onto and off of these parallel plates. So there can be currents that will carry these charges in and out, and we'll be building up charges on top of our plates. And the other salient connection to the outside world, just like in our resistor circuits, will be that there will be a certain well-defined voltage across our device, across these terminals that connect us, that will ultimately allow us to define the device characteristic associated with this type of a parallel capacitor device. So let's try to quantify those terminal characteristics. For those terminal characteristics, as we said, a certain amount of charge will have flowed onto our device. And let's just imagine that we've done things so that on this top plate, it just so happened that it ended up with positive charges. And we will characterize the net charge on our plate by the variable here, positive Q. Now, this system will want to maintain its approximate neutrality. We can't build up any significant fraction of a coulomb in any device, as you all know. So if we bring positive charges into the top, we are definitely going to be bringing a corresponding amount of negative charge onto the bottom plate, and we will call this charge then minus Q, like so. And if we want now to characterize the terminal characteristics of this, what we want to be able to understand is these terminal characteristics. We're going to want to be able to understand then how the voltage across these plates, namely the voltage from the bottom plate at point A to the upper plate at point B. And when we talk in general about capacitor devices, our convention will be that when we think about the voltage, we'll always be going from the negative plate to the positive plate. To try to comport with our other considerations of how a battery, we look at the minus terminal going to the plus terminal is the EMF, and how we track the upstream and downstream sides on a resistor. This will help us to keep our signs straight when we begin to do a circuit analysis. So this is our job then, is to calculate this voltage for a given situation, a terminal characteristics situation, where we know that through these terminals, right, our connection to the outside world, a certain amount of charge has flowed on, and we're now asking the question, what will this voltage be in general under these conditions? Now, we know our basic definition of voltage, of course. We can practice with this. It's minus the integral. It's minus because it's associated with work done by us of the electric field going from point A to point B. The electric field is a vector, and dot dx or dot dl. some little distance as we transport ourselves and drag some charge from the bottom plate moving up to the top plate. So we're going to be integrating in this direction from A to B, taking a series of little steps, as we usually do for these line integrals. Now, to evaluate the integral, of course, we will need to know what the electric field is doing. We actually have analyzed this in our exercises. We know that the electric field is independent of distance from these large plates that we can model as infinite sheets. We know the electric field down here is pushed downward because of the top positive charges repels them, the lower negative charges attract them, so we get twice the field from either sheet of charge alone, both in the downward direction, so we know there is a downward electric field E. And we also happen to know the value of the electric field, as we'd worked out previously. It's twice what we would have for an infinite sheet. The infinite sheet has a value of sigma over 2 epsilon naught for the sheet, but we have two of these sheets working coherently together so that our 2's cancel, and the electric field is just sigma on epsilon naught. Now, we can use one of our previous results, which was that for a nice constant electric field, this voltage integral, which we have done in the past, this voltage integral, particularly when E is constant, just comes out to be the value of the electric field times the distance over which you are integrating. In this case, that distance is just the separation between the plates D. And because we are moving against the electric field, there's a minus sign in the dot product, which cancels the minus sign outside of the integral. And it's our usual situation that when we are moving upstream against the electric field, we end up with a positive contribution for our voltage. So that's our voltage. We now just have to substitute in for the variables which we are given. The electric field is sigma on epsilon naught, so that's divided by epsilon naught times the distance d. I haven't written in sigma because we aren't given the charge per unit area sigma of our sheets. However, we know the total charge from our terminal characteristic. We know the total charge Q. We know the area of the plate, and sigma then is just charge Q per unit area. So our final result then for this terminal characteristic is that this upstream voltage across the capacitor from the minus to the plus terminals has the value of here. Let's just rearrange things in terms of our basic variables. Let's factor Q out on the front. Let's move Q out to here. And then what we have left behind is D on top. A goes into the denominator, as you can see, and epsilon is already in the denominator, epsilon naught A times Q. So that is the basic terminal characteristic for our parallel plate capacitor. It turns out that in common electrical engineering thinking, people like to think of use these devices actually to store charge and energy in an electrical circuit. So the greatest concern is not necessarily so much the voltage, but the capacity, hence the name capacitor, the capacity of this device to store charge. So the question that's typically asked is, well, what is the charge Q? How much charge can you store for a given amount of voltage? So this formula is frequently turned around. When we turn this formula around, then, what we are usually then trying to determine is the amount of charge stored Q. We can solve this equation simply by flipping this fraction upside down as we move it to the other side of the equation. So then we would have epsilon naught A over D times our voltage from the minus to the positive terminals. And this proportionality constant is given a name. This is called the capacitance of the capacitor, its capacity to store charge. A large value for this variable, typically called C, would mean that for a given voltage you have the capacity to store a large amount of charge. So we now have our classic characteristic equation to describe this circuit element, and we also have derived here the value for the capacitance In the case of a parallel plate capacitor, it has the value of epsilon naught times the area of the plates divided by their separation. So let's just put a box around these key equations for a capacitor. The top one is a general result, and the lower one is for parallel plate only.